please raise your question to challenge the reporter.
So we would like to challenge question number 7 to again.
Question number 7. So question number 7 is, please write the name of your representative who will speak to the hall.
So is this correct?
the projectile will eject it forward. And here's the theory. Because the ruler is illicit, so we need to consider the deflection and the Young's modulus. And the bending moment, after 2 times of integration, I can get a deflection, which represents the vertical deformation of the ruler. And from the last equation is from here. And that equation is the equation that represents the ruler is subjected to a single point force. And in my experiment, I have 2 F4 points. So it will be 2 delta plus together, which is the deflection. The delta is the deflection. And in my experiment, I have 2 F4 points I have just mentioned, and I define it as an x and an x1. And from observing from the x point, I can get delta x1, which will be caused by the delta 1 and delta 0. And from observing from the x1, I can get a delta x0. And after plussing these 2 together, I can get this formula. And it will be minus is because my f0 and f1 is the opposite direction. So it will be minus. So after rearranging, I can get this formula. And I rearrange it again, so I can get a f0 and f1. Because according to the Torrance statement, the parameter that they want us to be comparison is the velocity. So I can use f equal ma to get the acceleration and do the integration again, so I can get a velocity. And this part is from 0.12 to 0.13 is because my projectile and the ruler will be contacted then at only 0.12 to 0.13. After 30 centimeters, the projectile will eject forward and will not be contacted with the ruler. And here comes the experiment. Before my experiment, I need to define the condition that the projectile will be ejected forward, which is the force that pushes the projectile forward will be bigger and almost equal to the maximum state deflection. And after derivation, I can get the tangent theta bigger and almost equal to the coefficient of state deflection. And I put x and delta into the formula. I can get tangent theta equal to this equation. And put it in, I can get that equation. The reason why I'm doing this is because I need to compare my experiment and theoretical data that I can know the condition under the projectile can eject it is the same. So after my experiment, I found that it's highly fit. So I can prove my experiment and theory is fit. And here's my experiment setup. This is a launcher. This is a launcher. And this complex launcher is to make sure that the force that pushes the projectile forward will be horizontal to the floor. Oh, and I can measure that when I'm giving the ruler a force, I use spring. So I can calculate the force that I give to the ruler. And for my experiment 1, the independent variable is the level of x1, which is the fixed point to the F4 point step. And this is my experiment data. We can see that from my experiment data, when the x1 increase, the initial velocity also increase. And this is a comparison between the experimental data and theoretical data. And we can see that if the x1 is smaller, the error percentage will be bigger. And this part I will be explaining in my discussion 1. And for experiment 2, the things that change is the radius of the projectile, which is the arc length. And the parameter that will also change is the deflection caused by the changing of the radius of the projectile. And this is my experiment data. We can see that when the radius of the projectile increases, the initial velocity also increases. And from the comparison between the experimental data and theoretical data, we can see that when the radius of the projectile increases, the error will also increase. And this I will be explained in my discussion 2. And for my next experiment, which is experiment 3, the independent variable is the material of the ruler, which parameter that will be changed is the Young's modulus. And in my experiment, this is a prerequisite. We can see that when I change the material of the ruler, the coefficient of state deflection and the coefficient of the Young's modulus is larger, the initial velocity will be greater. And here's a comparison between different Young's modulus to the initial velocity. We can see that there are some errors between my experiment data and theoretical data. But one thing I can measure is that the Young's modulus doesn't really change my error percentage. The error percentage is almost the same. So the Young's modulus doesn't really measure the error. And here comes my first discussion. My first discussion is that I want to explain that why the x1 is smaller, the error percentage will be bigger. So this is the BT chart in my experiment. We can see that I have two sections of acceleration. For the first section, if it has acceleration, that means the projectile and the ruler are still in contact. So which means that the ruler will still give the projectile a force that pushes forward, so it will have acceleration. So this part has two sections of acceleration. And the first section of acceleration after my observation, this part of acceleration is the part that the center of mass is still within two rulers. And for the second section of the acceleration, the center of mass is already out of my two rulers. But this is a difference between my experiment and my theory. In my theory, I assume that when the center of the mass leaves the ends of the ruler and the projectile will not contact. But in my experiment, when the speed is too small, the ruler and when the center of mass is already out of the ruler end, it will still be contacted, which means that it will give it a force that still pushes forward. So we'll have a second section of acceleration. So after my correction of my theoretical data, so I can see that the percentage have been lower. So which means that this thought is right. And we can see that the percentage of 11 centimeter that part didn't change. It's because that the 11, this part, the velocity is fast enough. So the second section of the acceleration won't happen. And for discussion 2, I want to explain that why the radius of the projectile is larger, the arrow is bigger. And in my experiment and theory, my experiment is that this part to this part is a curve, but in my theory, this part is a straight line. So in my experiment, I observed it again. So I found that when the x1 is smaller and the r is bigger, the error between my experiment and theory will be bigger. So I modify my theory again. So I changed a straight line into two straight lines to image it into a curve. And I do the correction again, so we can see that the error percentage have been lower. And for this chart, the error percentage didn't really change a lot. It's because the radius of the projectile is only 1.5. It's not the largest radius. And this is the correction of experiment 2. We can see that for the 2.5 centimeters radius, the percentage has been lower a lot. So, yes. And here comes the conclusion. In my experiment, I can found that when the anchor point and the fixed point is further, which means my x1 is larger, the ejection speed will be faster, and also the radius of the ball is positive correlated to the ejection speed, and the Young's modulus is positive correlated to the ejection speed. And from the arrow part, I can know that when the anchor point and the fixed point is further, which means the x1 is bigger, the arrow will be smaller. When the radius of the projectile is greater, the arrow will be greater. And also, the value of the Young's modulus doesn't really matter my error. And the conclusion in my discussion part is that we found there is two sections acceleration if the initial velocity is smaller than the speed each two ruler poles. But if the velocity is bigger than the speed that two ruler poles, there will not be the second section of acceleration won't happen. And also the error caused by the geometric approximation can cause the theoretical data to be smaller than the experimental data. And the error caused by it would matter if the anchor point and the fixed point is neither, which means that x1 is smaller. And also the radius of the projectile
consider this as a experiment that is related to the pendulum.
Yes.
So next, your derivation. Next. So you wrote x1. What does x1 mean?
X1. You mean X1?
Yes.
It's the position that that the ball gives the ruler a force. This one.
Okay, in your theory, do you think that the force that you apply is the same across the room?
You mean in my experiment, one-time experiment? Yes, I give it the same force.
I mean, if you apply force at the end of the room, is that the same force that is in at the other end?
Sorry, what do you mean?
My meaning is that the force average through the room.
Every through the ruler.
Average. Never mind. So, talking about your graph. So, what are some of your error bars? What would you say?
Probably it's not all the same, but it's almost the same.
Okay, thank you. So, let's see your experiment setup.
This one.
So, how do you exert the force on the string?
I push these two springs, and from the deformation of the spring, I can calculate the force I give to the ruler.
Do you friction as a possible derivation in the series?
You mean the friction between the ruler and the
Thank
projectile?
God.
I can consider.
So then you have 3 minutes to prepare your talk. start.
Okay, so I'm the opponent from GGWP. I'm going to oppose and rebut some of the points reporter raises. So this is the problem statement, and their focus is on the relationship between the ejection speed and the deflection coefficient, and also the Young's modulus. Phenomenon is that given a ground projectile and a force, and the projectile will be ejected. And they use a series of deflection equation, vertical deformation, and also they use F3MA, and the A equals, A has two sections of acceleration using the center of mass location, and also their experiment uses a setup that measures the force using springs, and also during the experiment they change the effort point and also fixed point distance, and it also changes the radius of the projectile and also the material of it. And as for the pros and cons, the reporter has a really profound consideration on the curve of lunar and reality and experience, and also she has really clear graphs and also rigorous experiments. However, the reporter lacks clarification and notations, and also a lack of preliminary experiment to calculate the Young's modulus, and also they should consider the permanent deformation of the core. As for the discussion questions, these are a few points that I want to raise in the discussion. So first, are there any energy loss during the ejection, and also how to calculate the error percentage, the method, and also why is the second acceleration always bigger than the first? And for a phenomenon, about how to make sure that F1 and F2 x at the same time, and also what defines the initial velocity, the definition, and also how far the ball will be after ejection, and also the definition of error percentage. And other points include the R squared and graphing, which they didn't include, and also why the error bar are all similar, and also why the minimum velocity that the second assertion will occur, and also with bigger radius, could there be a third and fourth acceleration line? So I would like to invite you to work. Okay, so we're talking about your theory. So in this theory you propose you were using theory. The force is supposed to be force at one point. So it's the force in your experiment exerted at one point or another.
The force that I exerted to the lunar is only 1 point.
Can you show that as the experiment says? Okay, so you press the ruler at the spring?
Yes.
But that's an area, that's the point.
Yes, but in my calculation, I calculated into a point of view, and I have do the correction and calculation. I found that this doesn't really matter a lot, so I ignore it.
So talking about this, you said the error percentage. So what is your definition of it?
That you mean this error percentage?
Yeah.
My error percentage is from an experimental data minus the theoretical data and divided by the theoretical data.
But 17% seems to be high.
Yes, so I do the correction in my discussion. And for the guess,
back to your so you apply force at the middle.
I have changed the position that I exerted the force in my experiment 1. My experiment 1 is that I changed the position that I give the force to the ruler.
Can you ensure that the force that the ruler experiences is the same throughout the ruler?
The force that I want to mention is that how much I give to the ruler and how much the ruler will give it to the projectile.
However, if you use bending moment, the force should be the average force at the point, not the point, not the force that you exert after the equation.
You mean, sorry, can you say it again?
So you use the numerator in series, and the force is not the force exerted, but rather the force that is average throughout the.
Yes, but my projectile is put here. So the force I need to calculate is the force that how many will the force that the ruler give to the projectile.
Against your derivation of the deflection.
Maybe which part?
Back.
Okay.
So I see in your derivation you did not include friction.
I did not include friction. The part I include friction is when I change it into a velocity.
So do you think friction is a really important thing in this experiment?
I think the friction will affect when the condition that my projectile will eject it or not.
So as for friction, how do you calculate the friction coefficient?
I calculate by myself. I put the ruler here and the projectile here, and I put a plate down the ruler, and I stick the ruler on
Okay,
it.
thank you. Are there any errors that could happen?
Any errors that happen in my calculation, my friction?
Yeah.
I think maybe it would, but it would not affect a lot because I do a lot of time and it is almost the same.
So as for this experiment, what if the ball already launches before the ruler closes?
The ball launches before the.
What if the ball launches before the ruler closes? Does that mean that some energy will be lost inside?
In my opinion, I don't think there will be energy loss. Only if my ruler will already be deformation. And the part you mean that the ruler close and the projectile ejected before the ruler close is the part that I mentioned, that the part that don't have the second section of acceleration. Like the velocity is too quick. So the velocity is quicker than the velocity that the projectile project forward. The projectile ejected forward will be quicker than to ruler close.
I think you should consider the minimal energy loss doing this, because as you can see, error percentage is still not zero. There should be energy losses inside this experiment.
But if I want to prove that the error is caused by the energy loss, but I don't think it will have an energy loss because you can see this part. This part is only for 4%. It's really small already. And after we did.
However, there are still errors. It's not like 3% or 2%.
But the theoretical line is already in my error bar. So which means that when I'm doing my experiment, some data is already on my experiment. It's already here.
So do you consider air resistance as a force that?
Yes. I didn't consider air resistance in my theory because I did a calculation before, and from calculation we found that the air resistance, the ratio of the air resistance and the force is 0 to 0.00159. It's really, the ratio is really small, so I think the air resistance can be neglected.
So what is T1 and T0?
Is from this beauty chart, and one part is that I have the calculation in the air resistance, and the other is that I didn't calculate the air resistance.
Now talking about, okay. So do you think that the ball would rotate during this launch?
In my experiment, I did observe it before, but in my observation, it won't rotate a lot, so I neglected.
Do you consider that as important?
I didn't put it in my report.
But I think the ball rotating means that there's friction actually.
Yes, if my projectile is rotating, that means the lunar give the normal force is not the same.
It's not the same. So, how do you measure the friction? How do you measure the force that acts on both?
But in my experiment, first thing is that we didn't. In my experiment, the rotation is really small, so I want to neglect it. The second is that the two rulers I use have the same Young's modulus, which means that the deflection between these two rulers will be the same. So the normal force will be almost the same. It have really a little different, but it won't affect a lot because I proved it when I see the observation video. The rotate is just a little.
So if you said that it will rotate, do you consider the rotational energy as part of it?
But I think it won't really matter.
So are there any boundary conditions that about how many force would it cost to eject?
I have now four. In this condition before the condition under the projectile can be ejected. Actually delta x1 can be generated to f1, but the part I show here is the delta x1 and the f1. So
What do you mean by F1?
the x1, the place attached. The place attached.
And then how do you define the initial velocity?
In my experiment,
In your definition.
my definition, when it started to eject, and the time that it started to eject to it leave the ruler, that moment, this short moment, maybe just 2 centimeters or 1 inch.
So, talking about the theory, do you consider the kinetic energy of the ruler as part of the equation?
No. You mean like this?
Yeah.
Because I can't just put this into integration. So I need to calculate the v. I need to calculate the velocity. So I put the acceleration here. So it will be equal to the kinetic energy of projectile. So I can get a v.
However, I think that there should be vibrations on the ruler, and so that the ruler has kinetic energy.
I think it can be neglected.
Why?
Because it just affects a little. And from our data, we can see that my theoretical data and experimental data already is very fit. But I don't think there will be a lot of error.
So, what will be the minimum velocity of the second acceleration?
The minimum velocity.
Yeah. So you talked about that you have two acceleration lines. So, what will be the minimum velocity?
Minimum acceleration or minimum velocity.
The false minimum velocity.
False minimum velocity is a place that is a condition that under the.
Okay, time's up.
Thank you.
Summarizing, I am the reporter discuss about the error bar and also error bar percentage, and also the use of friction inside the engine, and also what energy losses could be seen in this experiment, and also the resistance effect on the ball. About the spinning or rotation, about that it includes friction, and also that it should include probably rotational energy, and also the boundary conditions that makes the ball launch, and also the definition about the initial velocity, and as well as the vibration of the ruler, and also the minimum velocity of acceleration. How is the second one bigger than the first? And we believe that energy loss is a really important thing to consider.
Okay, with your research.
How to define the low loss?
The low one. So much, when it started to move. In our experiment, when the force I give to the ruler will be equal to the maximum standard deviation, it will almost bigger and almost equal. It will start to lunge.
Okay, so do you think so? Do you agree with her? How do you define the low lunge?
Lunge is at the instant that the ball releases from it.
Okay, then where does the maximum or minimum speed occur, and what does the graph look like?
You mean what condition?
The position.
Or the position? When the maximum velocity will occur when the ruler stop contact with the projectile. Means there is no more acceleration, so it will be same speed that ejected forward.
So what do you think the graph is according to the different position?
I have a graph, I have a VT graph that
I'm
shows.
not talking about the graph. So what do you think about if you change the position of the force, and what is the velocity according to the position, not the time?
The position, I think with the larger the x, the distance between the force and the ball, the larger the velocity will be.
Can you say again? Sorry.
So I believe that the distance between where you put the force and the ball is larger when the larger the distance points of force and the ball will result in a larger velocity.
Okay. So do you know my example now?
In my experiment, when the fixed point to the echo point is longer, the velocity will be bigger. Yes.
So also that's a good.
Yes.
That's all.
So the reviewer, you have 2 minutes to prepare your report.
Hello, I'm Ian from the team Miracle, and I'm the reviewer. Okay, this is the problem recap, and the key point is that relation between ejection speed and ejection coefficient in Young's models. And I want to first talk about the overall of reporter. The pros is that she used spring but not her hand to do the force, so it can be calculated. And then she explained the theory with a lot of pictures, which makes it easier to understand. And the third one is she first discovered a flaw in her theory, and then she refined it and improved it. Things she can do better is that she didn't label all her data on her graph. And also, there's no exactly formula of the curve from the theory on her graph. And there's no preliminary experiment to know the Young's modulus. Okay, and then I'll talk about the overall opponent. And he asked about a lot of things which the reporter thinks that this is neglectable. The key discussion, the forces on the opponent asked the reporter that the force is on one point or multiple points, and the opponent thinks that the setup shows an area, but the reporter refuses. She thought that this doesn't matter a lot, and they use 1 point to calculate. The next question is friction important? And the opponent asked about how do you know the friction of the ruler? And the reporter says that she calculated the friction of the ruler by herself, and she thinks she do it a lot of times, and there is no error. The next one is about the energy. The opponent mentions that there should be energy loss in this experiment, and I agree this. But the reporter thinks that there will not be energy loss, and also later she later thinks that there's only 4%, and she also neglects air resistance. And this is our question. First one is how to define the velocity change. The opponent answered that the instant ball release. The reporter answered that the velocity change. We agree with the opponent. And the second question is the position influence the initial velocity, like where the force is doing on the ruler will influence the initial velocity. And the opponent says that when the distance gets bigger, the velocity gets bigger, and also the reporter agree with him, but we think that there is a U graph and there will be a maximum. That's all.
Okay. Reporter, summarize.
Thank you for the opponent and reviewer. There's a concluding remark, and in my experiment, the conclusion is that when the F point and the fixed point is further, which is like the radius of the projectile, both of them are positively correlated to my projection speed, and also positively correlated to the Young's modulus. And there will be a two-section acceleration, and the two-section acceleration will only happen when the velocity is too small. And the geometric approximation will also cause the error. And here's the concluding remark of our discussion. And I want to mention is that we think the friction will matter, so we put the friction into our theory and do the calculation with friction, with the dynamic friction. And we had calculated air resistance, and we found the ratio is small, so we neglected. And after our observation, the ball won't rotate a lot, so we neglect the energy loss caused by the rotation of the ball. And the initial velocity, the definition of initial velocity is the velocity when a projectile leaves the ruler at that moment. And we did calculate our Young's modulus, but we hide it at the back. And this is the calculation for our Young's modulus. Thank you.
Okay. So, question from the floor?
ejected velocity. So, yeah, smooth velocity means the higher than
Yes, it will be more
means
easy.
more rigid.
Larger Young's model means that it will be easier to be bended.
More can be over.
Yes, and more.
You agree?
No, like she says it in the opposite way.
Yeah, I agree with it.
Please.
So then, you both tell me what is the minimal condition that the object will be bounced by the balloon?
I believe when there will be a friction threshold when the ball is placed inside the loop, and once the force overcomes the friction, the force caused by friction, it will not change.
Yes, and we think that when tangent theta is bigger than mu s is from longer vortices, we are
Your other
In my opinion, if I give it a big force and it will eject it faster. So in my experiment, I only give a force that is almost equal to the maximum state deflection. So which means that it will eject it that moment. If I give it smaller, it won't eject it.
So when talking about errors, we have systematic error and random error. So which one is responsible for the error bar that we observe in the reporter's result, and which one is responsible for the discrepancy between the predicted result and the real experimental data. So my question goes to three groups, and three starting from the opponent.
So I believe that the difference in result in the theoretical data and experimental data is caused by is caused by human errors, and the other is caused by the energy loss that occurs in this experiment.
like the arrow bar and bird report is like I think it's the same or just a little different. So I think she just considered the type that's caused by the machine also.
In my experiment, my error bar is that what data I do about 5 times or 6 times, and the error bar is from my observability. And the press I give it is not the same when I'm doing the same data. So the uncertainty is from here.
Further questions? No? Okay. So please prepare the slide. Ready? Okay. So please show your mark on the 6, 6, 4, and 7. And for the reviewer, 6, 6, 6, 6, and 7. Okay, great. So that concludes the fights for this afternoon. Thank you very much. I'll see you tomorrow. Thank you.
好，请各组的 reporter， 然后来过来我们这边，我们要 copy 一份你们报告用的档案。然后桌上的笔，然后跟我们的 laser pointer 就帮我留在位置上。那老师的名牌还有我们的积分表也帮我们留在位置上。